Well, I will begin with a word of prayer, more or less time. So, Dear Father, we thank you again for this class. I thank you for this time we have to meet together, study your creation. Just pray that we'd help us use this time wisely, and that we glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, I want to talk to you guys about some new stuff today, but I figure probably for the sake of your best outcome on the final, it would be helpful for us to just take a second to walk through the test that happened yesterday. Sadly, I have not graded the test yet. I fell asleep, and it's exciting but true. But let's see here. But anyway, I should certainly have it back for you Monday. So, disclaimer, it's possible that I've made a mistake in my solution. I did go through it somewhat slowly and carefully. So, I mean, hopefully these are right, but it's plausible that you have a different answer and are still correct, and I'm just missing a sign or something here. All right, so if you see something, say something. All right. So, slightly different. Sorry about the math copier has fuzzified things lately. I don't know how to fix that, but he's like, well, why don't you just send it directly rather than copying a copy? Well, there's this thing with the stapler that, like, when I first got here, I tried to make 20 copies with staples and send it to the printer, and then I got back 20 copies without a staple, which meant for the next hour I was just 1, 2, 3, 4 staple. I'm very slow at this kind of thing. And then the rest of the professors made fun of me. They're like, what, you don't know to just make one copy and then copy it at the copier? I'm like, no, I did not know that. There's no sign above the copier that says, hey, don't try to send large orders with staples to the copier. So we end up making like one copy and then copying it. So when we do that, we get all this like fuzzy stuff from the copy. But anyway, all right, I think I ran out the clock enough for everybody to be here. So this one, basically the point is, if we look at the region of Pac-Man, you know, the blue shaded part, the boundary of that is got to be what? It's got to be like this way on the outside, which C is, that's good. And then it's got to be the opposite way on the inside. So the C1 is opposite the orientation, and C2 is also opposite the orientation that you want. And as such, that means that the boundary of R is given by C union with the reversals of C1 and C2, which when we apply Green's theorem in the data, we get that the integral around the whole boundary is 0, but that gives us that the integral around C is equal to the integral around C1 plus the integral around C2, which you might have just written down directly, and that's fine, because that is the deformation theorem, and you're well within your rights to use it here as it is appropriate, since the orientations of C1, C2, and C are comparable. No, it's not conservative. We have an integral around a loop is non-zero. That was one of our list of equivalent characterizations of conservative vector field. Integral around loop has to be 0. So it's not conservative. This here, this is just, there's nothing fancy here. This is just a straight calculation. You literally just take dx, dy, dz, plug it in, put in what x, y, and z are into here, here, and here, and integrate. And I would wager most of you got this one right. But then again, there's always surprises for me when I grade. So, and I have not graded it yet, so I really don't know who got that wrong or right for the most part. Problem 4, if you got this divergence wrong, I kill you. I don't know. If you put the divergence as a vector, I'm not even going to like put comments on your test. I'm just going to I don't know. Like half of you were making the divergence a vector on like the quiz, which was like disturbing to me, like very disturbing. So hopefully that did not happen. Again, I haven't looked at the test. I really shouldn't go so heavy into this comment. I may regret it. You guys can still drop the course, right? Yeah, don't drop the course. You'll probably pass. So I'm just joking. It's very rare for anybody to stick with the course and actually do everything and still not pass. Now you do have to come to some understanding, right? Like you make a 40% on the final, then I'm still duty bound to like not pass you. But anyway, let's see here. So the curl, I'm sure that a lot of you got this mostly right and had like a sign error on like this one or something. Hopefully I haven't made that sign error. Notice the minus minus gives you a plus. Let's see here. Hey, now if I help you're studying and you really want to, you're welcome to come to my office hours today, and which might not be in my office. I might be in like the math conference room. Do you guys know where that is? Math conference room is in the math department. It's like there's like a conference room. It's like 20 feet that way, practically. And because I need to work with a student on a paper, so I'll probably be in there with him. But if you wanted to like take pictures of your test so that you could study on the basis of that, you're welcome to, if that would help you. Anyway, inevitable. Can I change answers on my test? No. Anyway, this one is conservative. There's the potential. xy plus xz plus yz, right? How did I get that? Truth be told, I guessed, right? I mean, I integrated, but what is integration but guessing? Well, it's educated guessing, right? So, and then we use FTC for line integrals, and I got minus 12. I hope you guys got that. I know some people did. Now, I think pretty much everybody got this problem wrong, including me. Last time I did it, like I assigned this problem before, if I can find it. So let's see here. So if we look back, this is the, I don't think I changed it. And so if you look at this version of it, I got a -1, but I think that's wrong. And for me, the mistake I made in this one, can you find it? If you look here, minus partial p partial y, right? What's p? 1 minus y squared. What did I do? I neglected the minus, right? So with that change, that becomes a 2x plus 2y, which makes this 1 plus 1, which makes this 2. And then when you sort through everything, I think you get a -3. Let me go back to my actual solution here. So anyway, I'm sympathetic if you made that kind of error. It's going to take me a minute to see the difference between that kind of error and like an actual serious conceptual error. A lot of you, I think, just did Green's theorem with the hope that that would be the answer. I don't know. So I got 2, and then, but see, that's the integral of minus the curve plus C2. The thing is that you notice that the curve that's given is clockwise. So that's actually minus the curve that you're interested in. I mean, the Green's theorem gets you in contact with minus the curve that you're interested in, annoyingly. So, you know, if I pull this minus out, then, well, I could still be wrong about that. I'm not 100% sure. Let's see, if I subtract so that integral of C2 is 1, right? So I subtract that to the other side, I get 1. I should be -1. I made it, this is wrong, right? This is -1, which is what we calculated when you talked to me, Violet. Like when we corrected your calculation, you had like one small dot product error, and then it worked out to -1. Yeah.
It worked out to something I didn't get.
So wait a minute, was my last solution right, but for the wrong reason? Oh, weird. Anyway. These are things I have to think about. But anyway, typos and sign errors aside, do you understand the method here? Right? If I had a problem like this, you'd be good. Let me show you the problem I almost assigned, but I deleted it for the sake of the test. I think I deleted it. Goodness gracious. Well, I got rid of that one.
That was a different problem.
Yeah, that was a different problem altogether. This one I got rid of. But I almost put this one on your test. So here you have a half annular region, and again, it's basically just a straight Green's theorem problem. However, it requires like a polar coordinates approach to do the integral. You were ready for this one? Gah, well, maybe it'll be on the final. Let's see here. All right, so going back to the actual test 4 here. I guess I'll have to correct my solution on that last one. I think it was -1. Ah!
The square was different on the test.
The what? The square was different? I think it's the same problem. I made a new square picture for it. So on the old test, I just drew the pictures in by hand and copied it, which I do sometimes. But anyway, so this one here, we've got the disk oriented upward and then the hemisphere oriented outward from the origin. So this is just a divergence theorem problem. The integral around the boundary of the half sphere is the integral of the divergence through the half sphere. But the divergence here is equal to, what was it? Oh yeah, 30 over pi, a very suspicious number. But that number was chosen so that when I multiply that by the volume of a half sphere, which is 2/3 pi r cubed, r is 1 here, so that's just 2/3 pi. The pi's be canceling, and you get 20, because 10 times 2 is 20. And then, let's see here, what else? Oh, and then I told you the integral around through the disk is 22, so I get 20 is equal to the thing we're interested in minus 22, which makes the answer 42. So there's your 42. I just gave a complex test. I made 3 problems work out to 42. I'm kind of proud of it, but in very non-obvious ways. You wouldn't see it coming. Anyway, that's a pretty standard divergence theorem problem. It was kind of like a problem on the math battle, sort of like that problem on the quiz. This was homework. There's a homework problem. Man, so loud. This is what Paul was talking about in his epistles. Let's see here. Okay, I'm joking. Mostly. Anyway, so here, in the homework you had one where you worked out directly from the definition of the surface integral, and then also from the divergence. I think the divergence calculation is easier. The direct calculation with like ds vector is also not bad, but I chose the divergence theorem. So the divergence of f here is 3, and so then I'm just left with the integral. I mean, really, you could have just said 3 times the integral of dv, but you know that the integral of dv is 4/3 pi r cubed because it's a sphere. Worked out that before. If you did that, that would have been fine. I wouldn't have taken points off. If you didn't actually slog through this integration and you just knew what time it was in the terms of, oh, the integral of the volume of a sphere is 4/3 pi r cubed, then in the context of this problem, I would have been like, fine, cool, you know that. But anyway, so 4/3 pi r cubed times 3 gives you 4 pi r cubed. Yeah. Let's see here. Then this one, we had the calculate the flux through the outward oriented closed surface bounded by x squared plus y squared equals to 1. The cylinder centered on the z-axis, right, is equals to 1, and that paraboloid z equals to x squared plus y squared. So it looks kind of like that. And again, I think divergence theorem is the way to go here. And as I'm looking at this test, I feel like I should have forced you to do a surface integral somewhere. It's kind of missing. That's okay. No. I'll bring it back in the final, don't worry. Let's see here. So actually, that's not true. There is a surface integral that you had to do where? In the Stokes theorem problem, yeah. So now here the divergence is 3x squared plus 2y plus 1, right? And this particular volume lends itself nicely to cylindrical coordinates. And so, yeah, I was looking back over my solution in 2018, and for some reason, when I wrote down the integral, I put the r squared up here and the 1 down there. So like my answer is off by a sign. It's like, how many errors did I make in that solution? Good grief. Hopefully I corrected them in the class. I have no memory of it, you know. But anyway, so we switched to cylindrical coordinates. And in so doing, we get 3, and there's an r in the dv, which is r dz dr d theta in this context, because I want the dz measure first, because we're integrating over z first. And then notice that this is eventually going to integrate from 0 to 2 pi, but that's a full cycle for sine. That integrates to 0. We can ignore that term. The other 2 terms are non-trivial, though. And when I multiply through the, where did this 1 minus r squared come from? Oh, this, yeah. When I integrate in the z, I just multiply by the length of the integration region, because there's no z. So 1 minus r squared, and then 1 minus r squared here, and multiply that out. And I got a 2 pi out front because I integrated the, oh no I don't. Well, I got a 2 pi out front on the one side because I just integrated d theta. But I've got an integral cosine squared theta d theta on the other. Since cosine squared and sine squared are symmetric about the interval from 0 to 2 pi, and I know that sine squared plus cosine squared integrates to 2 pi over all the way from 0 to 2 pi, it stands to reason that the integral of cosine squared is just pi. Because it has to be half of the integral of sine squared plus cosine squared, which is clearly 2 pi from 0 to 2 pi. So that cosine integral works out to pi. And this one works out to 3/4 minus 3/6, and that one is 1/2 minus 1/4. And then fractions. Stuff cancels. I got 3 pi over 4. The other year, I got minus 3 pi over 4 because I made the stupid mistake of putting the bounds wrong with 1 and r squared. So my mistake checks this answer. If that makes sense. I'll go on. Now, if you didn't get these things, there is partial credit to be had, right? But anyway, I want to show you. Then we're supposed to verify Stokes' theorem on this problem. So first of all, notice that on the boundary of the open hemisphere, we've got dz equals to 0, right? Because z is equal to 0 on the boundary. So the dz is fixed. dz is 0, so I can ignore that term in the line integral. In the line integral, I just have my minus y dx plus x dy, right? But x is cosine, y is sine, z is 0. So when I plug those in, I get minus sine, that's a use your imagination sign, minus sine t dt, cosine. So I get sine squared plus cosine squared, and we integrate to 2 pi. So that's nice. On the flip side, calculate the curl. And so the curl works out to 0, 0, 2. ds vector for a sphere is that, sine squared phi d theta rho hat, which works out like that in terms of the explicit Cartesian content of that. So when we take the dot product with 0, 0, 2, only the z component matters, and we just pick up a sine phi cosine phi times 2 d theta, which then we can integrate over the appropriate range of spherical angles, namely 0 to pi over 2 for the colatitude, and 0 to 2 pi for the polar angle, theta, and then we get, well, 2 pi. So
ds for a sphere rho squared sine theta.
it is, but it's a unit sphere. You're not wrong. It's just I put rho equal to 1 there. Now the last one I messed up But so there would be more generous partial credit on the last problem because my setup wasn't quite what I wanted. I had, I think I know what I did. I think when I calculated the ds in the last problem, what I ended up doing by accident was neglecting the, like I had a square of something and I got like a sine squared plus cosine squared, and I put a cosh squared next to it, but it was actually a cosh to the fourth, and that changed it. And that's the mistake I made when I was working out the problem before the test, and trying to set it up. So anyway, here we have a hyperboloid of one sheet, and so I would personally recommend parametrizing it with cosines and coshes and sinches like this. I think this is the easiest way to parametrize it. Of course, you could have used z, and if you did that, then you would have a radius of like the square root of 1 plus z squared. So you could in principle have like radical 1 plus z squared in the places of cosh. And sinh then would be, well, you just have z for sinh, right? That would have been also fine. That probably would have worked out. Anyway, so I calculate my partial velocities, like so and like so. The point of this problem was to give you something that wasn't on your formula sheet, right? Probably not. I mean your 3x5 card, I should say. I keep calling it a formula sheet, I'm wrong. Would you guys like a formula sheet for the final? All right, granted then. Yes, I already told Violet that she could have one, so if I let Violet have one, then it's probably kind of rude to not let you, the rest of you have a sheet of notes. But yeah, you can have a sheet of notes front and back, that's fine. Yeah. Let's see here. So, where was I? So I took the cross product of the partial velocities, and I got this bad boy right here, and then calculate the length of that thing. That's where I made my mistake in the setup. I tricked myself into thinking that should have been a cosh squared, which would have made this work out precisely so that the integral I gave you would have let you write it exactly in terms of that. Again, my mistake. Sorry about that. Anyway, so with that, I get this sum, which I can factor a cosh squared out of. Of course, cosh is always greater than or equal to 1, so you can pull that outside the square root without any worry about plus or minus. And that leaves me cosh squared plus sinh squared, but cosh squared is 1 plus sinh squared, which gives me cosh times the integral of 1 plus 2 sinh, which is what I should have told you this integral. Oh, really? Oh, cool. A u sub and a trig sub. You may be right. Yeah, that's right. Yes, we could have actually done that integral. Hey, I didn't need to give you an integral. Thanks, Sam. So I will grade it without partial credit because it could have been done. No. Do you guys know what he's talking about?
You can't find it in terms of beta.
No, you can't write it in terms of beta, but what he's saying is like integral of, so here's like a Calc 2 that you've probably forgotten about, but this is like the integral of, okay, so yeah. So let u equals to, I guess, square root of 2? No, just 2? Yeah. Yeah, we'll do square root of 2 sinh t just to make it easier on us, right? Somewhere you got to take the poison pill of the square root of 2, but I guess we could, so if we do that, then it's like, 1 over the square root of 2, square root of 1 plus u squared, right? Because so you'd have that, right? Which then you could let u equal to sinh t. Well, maybe not t, but sinh phi. Alpha, yeah. So then 1 plus u squared is cosh squared alpha. And the du, of course, is cosh alpha d alpha. And so you got 1 over root 2 integral of cosh squared alpha d alpha, which you can do. So yeah. Now, if you were not in my Calc 2 and you were in like any other Calc 2, you learned to do a trig substitution here, which leads you to secant cubed. Which of course you can do if you want. I don't here. Anyway, so that's your test 4. Any questions? Not really. Yes, no, maybe so. So next week we'll talk more about the, well, I mean, I guess we could, I kind of wanted to start the new stuff today, so I'm going to do that. What's it? What? Yeah, new stuff. New stuff. Well, you thought we were done? So for the remainder of today and probably Monday, I will talk about the calculus of differential forms. All right. So what's that? Is this on the final? Oh, sure. If you'd like. There's usually at least an extra credit problem on this in the final. Okay, so, and I will make up an extra credit problem so you can, if you want to do it, you can earn a few points, whatever. So, this course, we have talked about vectors and we've talked about vector fields. And this is one description of we can use to describe physics, engineering, whatever in 3 dimensions. And it works pretty well, right? We have dot products, we have cross products. But before all this, there were these things called quaternions, right? And the quaternionic product, it involved actually both the dot product and the cross product all at once. And so quaternions were like 1840, something like that. And so for a while, for some time, a few decades, people worked with quaternions as a method to understand how to describe, say, let's say, equations of math and physics in, say, 3 dimensions. But then that fell out of favor about the turn of the century, about 1900 or so, with the work of Gibbs and Heaviside. They popularized the vector formalism, which we still use to this day. But sort of in tandem with the quaternionic viewpoint, there is what you could call the differential forms viewpoint. And so differential forms are, let's say, a competitor to vector fields as a means to describe theories and equations and different models in space concerning, say, physics, engineering, whatever. They're like vector fields, but they're not vector fields. There's a correspondence between differential forms and vector fields, sometimes, but not always. In 3 dimensions, there's this really special correspondence between differential forms and vector fields, which only happens in 3 dimensions. In higher dimensions, it's different. So like, for example, if you wanted to study string theory, say, and you wanted to talk about electromagnetism in, say, 10 dimensions or something, you wouldn't talk about an electric and magnetic field. The electric field still corresponds to like a vector field in some sense, all right? Something that you could integrate along a line, but the magnetic field then is no longer in the same category. It's actually what you'd call a magnetic flux. So it's got a different number of components. Like there's this duality between electric and magnetic fields is modified when you get to higher dimensions. And the calculus to understand all that is differential forms. Differential forms give you a set of objects that you can study in higher dimensions that is not bound to the special accidents, happy accidents, which happen for us in 3 dimensions. It's not just string theory either, also like fluid dynamics, more sophisticated engineering, anything that involves really calculus on a curved space can benefit from the use of differential forms. So anyway, let's talk about it. So what are the differential forms in 3 dimensions? So let me just tell you what they are. We have 0 forms, we have 1 forms, we have 2 forms, and we have 3 forms, and that's it. All right, there's a 0 form, a 1 form, a 2 form, a 3 form. And I'll just, in each case, let me just write down for you what they look like. So a 0 form is just f. It's just a function. All right, literally just a function on R3. So you could say a function from R3 to R, just a plain old function. All right, a 1 form, which we'll say omega sub vector ABC is equal to a dx plus b dy plus c dz. So this correspondence, so here a, b, and c are all functions. Are themselves functions from R3 to R, all right? And this is the so-called work form correspondence that I just wrote here. So this right here, work form correspondence. So this is how I just was talking to you guys a second ago about the correspondence between vector fields and differential forms. This is one of those correspondences. For every vector field, there's a corresponding so-called work form. You just do a dx plus b dy plus c dz. We've actually already been kind of using that notation in this course, truth be told, right? Because to calculate the line integral of the vector field PQR, what did we do? We integrated pdx plus qdy plus rdz. So this notation, it plays nicely with that with the standard differential notation we use in Calc 3. 2 forms. All right, phi of ABC, and that is by definition a times dy wedge dz plus b times dz wedge dx plus c times dx wedge dy. And again, a, b, c are functions from R3 to R. This right here is the so-called flux form correspondence. All right. So, and you can kind of maybe already see the pattern. What is it reminiscent of? You guys?
Surface area.
Well, yeah, it does kind of look like something for a surface, yeah. But how about the correspondence? What's going on with the correspondence? What's A going? A is the x component. What's it going to? dy. First of all, you might go, what on earth are you talking about? Dy wedge dz, right? This is a new thing. All right, these are not. It's not like dy wedge dz is equal to dx. All right, let me just first say that. So dy wedge dz is not equal to dx. This is a new thing. It's a 2 form. So that's one big difference between the wedge product, right? Which I'm just going to formally describe to you today. We can construct the wedge product through concrete, well thought out mathematics. I'm just going to describe it to you today as like a formal system. In other words, I'm just going to tell you there is such a thing. Trust me that you can construct it. Lots of different ways. You could use matrices, for example, to construct it, or formal quotients in abstract algebra, whatever. That's not the point here. The real point for me is that it's not something you've already seen. All right, it's like it, but it's not it. See, because you guys remember how it goes. Y hat crossed with z hat is equal to what? See, it's equal to x hat. So the cross product is not the same as the wedge product. It's like it. We're going to see more of that in a second, but it's not the same. They're related, but they're not the same. The 3 form, well, there's just one of those, and it's this, g dx wedge dy wedge dz. This is any 3 form looks like that. All right? That's a 3 form. So let's talk about this wedge product. What's the wedge product? So let me just say it in words. The wedge product of a P form with a Q form is a P plus Q form. So sometimes the wedge product is called an exterior product because it takes in 2 things of a particular type and it gives you a new thing which is not of the same type. So, I mean, in that sort of general idea, the dot product in some sense is kind of like a wedge product. It's kind of like an exterior product in the sense that the dot product does what? It takes in 2 vectors and it gives you out a number, right? So it's not giving you back an object of the same type. In contrast, the cross product is a genuine product in the sense that the cross product of 2 vectors is again a vector, right? So, all right. And so if we have gamma and beta, well, let's say gamma, let's say a P form gamma and a Q form beta. Then we have this gamma wedge beta is equal to -1 to the PQ beta wedge gamma. So it doesn't, the way it works, it doesn't commute, all right? Not always anyway. Other things, the way the wedge product works is like if you have, say, gamma wedged with, say, C beta 1 plus beta 2, you get C times gamma wedge beta 1 plus gamma wedge beta 2. So this is, you know, it's not a commutative product. It is, however, it does, however, obey the usual like distributive laws. Here I'm talking about C being a constant, so you can pull constants out of it. You can distribute across sums. But the thing that makes it really, really different than the cross product is the following, which we just kind of, I don't know if you've ever thought about this or not, but the cross product doesn't have this. So if we have alpha, wedge beta, wedge gamma, that makes sense. And what I mean by that is that I can meaningfully write that before I add these. But if I add these, that brings clarity to what I'm saying. So I'm saying that this is a associative. It's an associative product. All right? So pragmatically speaking, you can basically construct these rules a few basic rules like dx wedge dx is equal to minus dx wedge dx, right? So since dx is a 1 form, that rule gives you that dx anti-commutes with itself. But what does that say about dx wedge dx then? So that gives us that dx wedge dx is equal to 0. Likewise, dy wedge dy and dz wedge dz is 0. All right? On the other hand, if we have dx wedge dy, That's minus dy wedge dx. And dx wedge dz is minus dz wedge dx. And dy wedge dz is equal to minus dz wedge dy. So these are the basic rules of the wedge product. In fact, if I just told you these basic rules and I told you that the product was like distributive and associative, you could work out the claims I have above it in general. Like you could build the wedge product from these basic assumptions, these basic rules I wrote at the bottom of the board. Let me show you an example of a specific one here. Let's suppose we have, oh, I don't know. Let's suppose we have like alpha equal to, well, I don't know, dx plus 3 dy plus y squared dz. And I have beta is equal to, let's say, x plus 2 dx plus e to the y dy plus 42 dz. There we go. Weird enough. I really should have just put numbers here. But I wanted to emphasize that the coefficients can be functions, all right? So if we calculate alpha, man, I regret making this so complicated. Alpha wedge beta, oh man, that was dumb. So how would you do it? Oh man, I regret. I regret my choices. So we distribute. All right, and let me just give this thing a name. I'm going to call that, well, it was beta. I guess I can call it with beta. So it's distributive. And then as you think about what you're taking dx wedge with beta, what happens? So like, let me just write it, let me make a comment on each line here about the part which has gone away, right? So like the dx wedge dx is 0, right? So x plus 2 gone, because dx wedge dx is 0, right? And this one, you've got your e to the y gone, because what? dy wedge dy is 0. And this we can neglect the 42 gone, because we've got dz wedge dz is 0, right? When you take that wedge product. So all that's left then is dx, well, e to the y, dx wedge dy, plus 42 dx wedge dz, plus 3 times x plus 2 dy wedge dx plus 3 times 42, which is 126 dy wedge dz, and then plus y squared times x plus 2 dz wedge dx plus y squared times e to the y dz wedge dy. So listen, I mean, all I'm doing is very, very simple, actually. I'm just obeying the usual laws of algebra, right? And taking into account this funky new rule that dx wedge dx and dy wedge dy and dz wedge dz is 0. All right? And that we can pull constants, or in this case, scalar functions out to the front. Now look at it. We can group things together. We've got dx wedge dy here, but we've also got dx wedge dy somewhere else. Oh, right here, right? But it's in the opposite order. See it? So when we bring those two together, we need to put a minus on one of them. And so I'll put a minus on the second one. So I got e to the y minus 3 times x plus 2 dx wedge dy. That's the orange ones. And then the red ones, let's say dz wedge dx. That's this guy and this guy. So that gives me plus y squared times x plus 2 minus 42 times dz wedge dx. All right? And then plus what? The remaining terms, the dy wedge dz, so 126 minus y squared e to the y dy wedge dz. Right? What is that, though? What's going on here? Let me tell you what's going on. What's happening is that what we started with was the work form. Oh man, worthless. The work form of a vector A, and this was the work form of a vector B, right? And what we have down here is exactly the flux form of the cross product of A and B. If you take the cross product of, in other words, if you calculate the cross product of A cross B, specifically meaning the cross product of 1, 3, y squared with x plus 2, e to the y, 42. What you will get is e to the y minus 3 times x plus 2, comma, y squared times x plus 2 minus 42, comma, 126 minus y squared e to the y. Now this example is not a happy accident, all right? Like, this is a general identity. So there's a theorem that I could write down. Omega A wedged with omega B is equal to the flux form of A cross B. So this is the way that the wedge product naturally includes the cross product algebra. All right? So if you take the flux form of A and you wedge it with another vector B, excuse me, work form B, what do you get? So let's say that the B vector is x, y. I need to come up with components for B. Let's say alpha 1, alpha 2, alpha 1 dx. What happens when we take this wedge product? We get what? We get A alpha 1 plus B alpha 2 plus C alpha 3 times dx wedge dy wedge dz. If you don't see that, let me just explain why that goes. So like the dx wedged with the b or the c terms, well, there's a repeated dx. So dx wedge dx is 0. Anything wedged 0 is 0. So the b and the c terms go away for the alpha 1 term. For the alpha 2 term, the a and the c terms go away because there's a repeated dy. For the third term, there's a repeated dz if you look at the a and the b terms, so only the c remains. And what is that? Can you guys recognize what that is? I hope you can. That's exactly A dot B. dx wedge dy wedge dz. All right, so there's a lot more to say, but that's where we got to today. I just wanted to start to show you that the wedge product automatically includes enough algebraic structure to recapture the cross product and the dot product. Next time I'll show you how we can do gradient, curl, divergence, line integrals, surface integrals, all in terms of differential forms. In fact, in terms of one unified integral. It's actually very beautiful. And the Stokes theorem, the divergence theorem, the fundamental theorem of calculus, they all become the same theorem, the so-called generalized Stokes theorem. So that's what's up Monday. Anyway, thanks guys.